There once was a school where the students spent all their spare time forming clubs. To prevent them from getting too carried away and neglecting their schoolwork, the principal made a pair of seemingly innocuous decrees. There can only be an odd number of students in each club. There can only be an even number of students in common between pairs of different clubs. What's the maximum number of clubs possible after the decrees were put in place? Take a moment to try this out for yourself. It'll be helpful for us to tabulate the students in the clubs that they are in. Let each row of the table represent a club and each column a student. We put a 1 in a cell if the student is in the club. We put a 0 otherwise. This is a common structure known as an incidence matrix, and it can be used in many settings to record the relationship between elements and the sets which contain them. As an example, in a graph, the vertices are the elements and the edges are pairs of vertices. Using incidence matrices, this is a possible example of a set of students and clubs. Here at least, it seems that the number of clubs is no more than the number of students. Is this indeed the largest possible, and how might we prove this? Let's denote the maximum number of clubs by m. Currently, it is an unknown. What we want is a relationship between m and the total number of students n, and we would like to find such a relationship by analyzing the incidence matrix. What happens when we multiply this incidence matrix by a vector representing a club, or one of the rows of the matrix, say the first one? When multiplying by the chosen row, we get the number of elements in that row. When multiplying by any other row, we get the number of elements in common between that row and the chosen one. We can consider multiplying the incidence matrix by every single row, or combining all the rows together to form the transpose of the matrix. What happens then? We get a matrix whose diagonal entries count the number of students in each club and whose off-diagonal entries count the number of students in common between the two clubs. Before proceeding, let's review the problem statement. We note that the two decrees only care about whether the clubs have an even or odd number of students and not the exact number of students. Thus, it seems eminently reasonable to replace each entry with its parity, the value of that entry modulo 2. In fact, we can perform all the multiplication and addition operations required to get the matrix product modulo 2. When we do this, the first decree is equivalent to 1s on the diagonal, and the second decree is equivalent to 0s on the off-diagonal. Hey, that's just the identity matrix! The identity matrix has many nice properties, but most importantly for us is that it has full rank. We would like to bound the rank of the product of two matrices by the rank of either matrix, since then we will be able to bound M by the rank of the incidence matrix. As we know from many a great linear algebra explainer video, multiplying by an m by n matrix is a linear transformation from Rn to a subspace of Rm. The product of two matrices is a pair of linear transformations applied one after the other. If one transformation reduces the dimension of the subspace, then the other will never be able to recover the lost dimensions. Thus, the rank of the product of two matrices is no more than the rank of either matrix. Now we have everything we need to bound the unknown number of clubs m by the number of students, n. As before, the number of clubs is equal to the rank of the product of the incidence matrix with its transpose. Now we know that since A is an m by n matrix, it can have at most n independent columns, and its rank is at most n. Thus, m is less than or equal to the rank of the incidence matrix, which is less than or equal to n, or the number of clubs is at most the number of students.